Okay, well, maybe time to start. So thank you, everyone. Welcome to this last internal ICCUB seminar of the academic year. And so for this last one, we will have by Mercè Romero. We hope to hear from her about these great results on the Magellanic clouds from the Gaia mission. So thank you very much, Mercè. Please go ahead.
Hello, so I share the screen. This one, share. Okay, so thank you very much for the invitation. I have, since the structure of this internal seminars are quite informal, I have divided this talk in two, so as to make this usual stop more or less at the middle. The first part is more or less a quick summary of the results of the paper that we published together with the early data release 3 of Gaia last December on the Magellanic clouds that we participated mostly in our team. And then on the second half, I will give an update of the new things that we've been pursuing in the last 6 months, which are part of the PhD thesis of Oscar. Okay, so I'll start with this summary. So the idea is that we have now astrometric data and photometric data of the Magellanic clouds. We have used this astrometric and photometric data from the early data release 3 to show the community how good this data is and what kind of science we can do focused on the LMC and the SMC. It was a challenge, or it is a challenge, due to the distance that the Magellanic clouds. It's more or less at the limit of the Gaia astrometry. I'll show you in a minute. But we can see that not only we have distances, we not only have parallaxes, which are more or less at the limit, we have also proper motions. And with proper motions, it opens a new window of science that that it was not done before. Also, not only in the astrometry, in the photometry. So we have colors for these sources. We have more than 12 billion sources in this region. We made 2 cuts, one centered in the LMC and the other one in the SMC. We made some filtering in order to remove background from the Milky Way halo and the Milky Way. So we have these 2 selections. We can see that for the LMC, it includes part of the SMC, but we did it on on purpose to get completely the bridge in between the two clouds, and the other one is centered on the SMC. So this is just some filtering on the astrometry. And we then, thanks to having the broadband G photometry and the 2 colors, we can do for the first time a selection based on different evolutionary phases. This is a color magnitude diagram of the stars centered on the LMC. We have the analogous for the SMC, and just draw some polygons on top of this CMD. Take into account that we did not made any correction for the absorption. This was out of the scope of this paper. We just used the photometry as it comes from the catalog, and then we chose different evolutionary phases depending on the age, the brightness of each sample. Let's say here we can identify very well the red clump, for example. This is the brightest part of the main sequence, so we can have different samples according to the age: young 1, young 2, young 3. We have the tip of the giant branch, the red giant branch, red lyre, blue loop. And we also have cepheids chosen from another technique. But only from the color magnitude diagram we can have these different samples tracing different populations. For the outreach team, let me try to play. It crashes. I'll restart again. The outreach team in Gaia the PAC made some videos for the release. These take the data of these different samples, and we just plot on the sky the distribution of these samples according to their different colors, and we can see how these samples show different structures or substructures in the LMC and in the SMC. For example, this is the red giant branch, also the red clam. Look, you can see very well the outline of the bar in here, the Rare, old population in the halo, asymptotic giant branch, also very old stars. And if we put them back all together, we can see this very nice colored structure. Okay. Another thing, this was a performance verification paper, a science verification paper. So for the EDR3, and we did some comparisons with the DR2, because in the DR2 was and also a collaboration paper that was focusing on dwarf galaxies, and LMC was one of them. And here we make a comparison of the astrometry and in the photometry. So on the first row, it is a color map of the parallaxes, proper motion and proper motion in the two directions in the sky for the DR2 paper, okay, from DR2. And you can see on the second row the improvement with respect to DR2 in the DR3. So again, parallaxes and the two proper motions. You can see that the systematics, we can see from the scanning law, are largely removed. These artificial lines here that we can see in the proper motion are largely also removed. So this is also a nice thing to show to the community, and not only in proper motions, but also in the photometry. We know, there is this index that we call the excess factor, that it's kind of an indication on the quality of the photometry. And this on the plot on the left is a sky plot on the region of the LMC and the SMC for the DR2 photometry, and the same on the right, but now with the EDR3 photometry. And we can see again that using the same scale, this large excess factor, which we would expect to be around 1, is considerably reduced. So the photometry also improves in this crowded area region. Okay, in this paper we tried to reproduce or try to infer the 3D structure of the LMC. We have not only the positions, but also with the parallaxes, try to infer the 3D structure of the LMC. This was a problem that was it's proven to be very difficult to crack. It's, as I said at the beginning, we are at the limit of the Gaia capabilities at these distances. So the observed parallaxes are at the limit of the noise, and we also have to consider this systematic of the 0 point on the parallaxes. So we made our efforts in the writing of the paper, but we did not succeed, and we reported these difficulties and complexities of the model. But this is one of the points that I'll show you in the second part, that we have been working, and we are trying to get some solution on this. But as I said, not only we have positions and parallaxes, we have the proper motions, and for the first time at these positions we can have a kinematic study of the motion of the LMC and the SMC. I'll show you the results for the LMC, which is the one that is known to have a disk and a cylindrical rotation. The SMC, it is more complicated. It does not show a clear rotation. It is a topic that's still under debate, and we focused on our results in this paper on the LMC. So here I show you the LMC. This is a plot of the LMC with the vector of the proper motions overlapped one on top of the other, and we can see that there is a kind of we can infer kind of the structure. If I didn't say you anything, maybe you can hint that the main overdensity is here, which is the location of the bar, and maybe you can hint here kind of the spiral arm. So the overplot the overdensities as the positions, we can see this overdensity also shown in the kinematics. For the SMC, as I said, this is more chaotic. We do not see a clear rotation or clear structure of this rotation, or this is an irregular galaxy, and this is also shown in the proper motions. Okay. One of the things we can do with the proper motions is try to infer the rotational center of the LMC. This is a key ingredient if you want to analyze the structure of the 3D structure of the LMC. We need to center the galaxy to be able to project it on the sky, and getting the center of the LMC is critical. We can see here that there has been different other studies using other photometric surveys or HST proper motions or carbon stars and other tracers of photometric surveys. You can see the differences in the sky can be of the order of a couple of degrees, and the 3 or the 4 colored points is the ones that we get with Gaia EDR3 data, using different selection of stars, but we can see that they agree very well around this point. So this is one of the things that we could report. The other thing is making velocity maps of the LMC, of our neighbor. We not only for the whole 12 million stars in the sample, but also separated by the populations. We can see that not only in the density, but also in the kinematics, the different populations show differences. So here in this plot, on the left column, we take one of the youngest evolutionary phases selected in the CMD I showed you before, and on the right for the typical red clamp. The different rows is that the bottom row is the radial motion, and the first row is the tangential motion. Take into account that we derived these cylindrical coordinates for the velocity without having line of sight velocities. So it is more or less the cylindrical coordinates, but we do not have line of sight velocities. But we do clearly see what we expect for a disk galaxy. Yeah? This is again LMC only. For example, this is showing the 2D projection of the rotation curve. We have zero velocity around the center. It increases and then it becomes more or less planar to the outer parts. The radial velocity is more or less centered at 0, but we see that it is not homogeneous. So we know that from these inhomogeneities in the radial velocity that non-axis symmetric structures exist in this galaxy. For example, the bar that we have seen. This is very nicely seen with the red clamp population, but it was also seen in the young population. You can see this quadruple signal of the galactic bar, like negative and positive in 2 by 2. And also for the tangential velocity, we have the trend of the rotation curve. If we make radial beams in this plot and we convert these two velocities, or exactly these 2D velocity maps into 1D map, we have the typical tangential and radial curves. Okay, so as a function of the radius from the center of the galaxy, we plot on the left the tangential velocity, so the top row of the previous plot, and on the right the radial velocity, so the bottom row from the previous plot. And here we have shown not only the red clamp and the young 2 populations, but all the different populations or evolutionary phases that we have in the CMD, we have selected in the CMD, and see the differences. Okay, so we can see that, for example, the rare rotate slower than the young population as expected. The dots are taken from literature values. The radial velocity, again, is centered on 0, but we have here a clear dip, for example, for the young population. Okay, so these are things that now we have to analyze and compare with the structure, with the non-axis symmetries, and infer the dynamics of the galaxy. More things, as I said, with the LMC, we have chosen, together with the LMC and SMC, we merged the two two and we now focused on the region in between, so the Magellanic Bridge, and the outskirts of the two clouds in the sea. You can see substructure in the halo, streams and kind of and these kind of things. The Magellanic Bridge is well known to exist in the gas. It was already detected in the 60s or 50s, if I'm not wrong, and it is a clear effect of the tidal interaction between the two clouds. So the large Magellanic Cloud is more massive than the small Magellanic Cloud. They are in clear gravitational interaction. So we have gas dripping from the SMC towards the LMC. From the stars, from the stellar point of view, we had some previous works using Hubble Space Telescope proper motions, some line of sight velocities, but we did not have a clear homogeneous sample as we have now with different evolutionary phases. So what we did in this paper is select the young 1 and young 2, add them together to have a young population. On the left, I show you the density plot with some isocontours to guide the eye. This is the edge of the SMC. Here we have the LMC, and we can see very nicely the bridge between of stars between the SMC towards the LMC. Why can I say towards the LMC? Because on the right, I have the vector of the proper motions shown in this region. And we can see that the stars or the young stars from the SMC flow towards the LMC and gets wrapped in the outskirts of the LMC. In dashed line, I show you some previous result that Vasily Velokurov published with TGAS data. TGAS data was the first release of Gaia, that we had some proper motions from Gaia and Tycho, and already envisaged these young stars with using young populations from TGAS. So we confirmed the results, and now we have increased the sample in the bridge. We did the same for the red clam evolutionary phase. On the left, again, it is the density. Here it is not so clear. You can see that the contours do not delineate so well a clear connection, density connection between the two clouds. It is more difficult to see this in the red clam. It is a more evolved population. It is kinematically hotter, it has larger velocity dispersions, and it's more difficult to see this evolution in the density because they can get dispersed more easily. But on the right, again, we show the vector flow of the particles in this region in between the two clouds, and again we see the flow from the SMC towards the LMC. So we can say that the connection, the gravitational connection between the two clouds exists not only for the young stars that would resemble the one from the gas, but also in a more evolved population. But it is more difficult to trace to put some dashed lines to see, okay, the bridge goes in this direction or has this width. It is more tricky. Okay, and for the outskirts, now we masked the two clouds, and we made some...
Mercè, I was wondering if maybe that is a good point.
I'm about to finish. Give me two more slides and I finish this part.
Okay, thanks.
Okay, I'm about to finish. So just to show you also the LMC and the SMC, as in many other galaxies, our galaxy and other galaxies, has also substructure in the halo. It has many streams and overdensities. And we can, the advantage is that not only we can plot them in density, but also in the proper motions. There is very few data, but things can be done in this direction. And finally, focusing on the spiral structure of the LMC, at that moment, we could only show some density plots. Here we choose the blue loop population, the blue loop evolutionary phase, which is very young, and we can see very well how this blue loop shows the bar and this only one arm spiral, which is kind of broken or bifurcation spiral arm. So yes, Jordi, this is where I can stop, and if you have any question of the results on this paper.
Okay, thanks very much, Mercè. Yes, we can have a pause, and anyone who has questions. Actually, maybe I'll just ask to start with, so for a brief overview of the whole thing. So, you know, because some people may not be familiar with, sorry, some people may not be familiar with the whole basics about the Magellanic cloud. So, you know, if you could say what are the sizes of LMC and SMC compared to each other, Milky Way, where are they orbiting? Why is it important to study this bridge, and what is exactly the bridge between them?
Okay, so LMC, I don't have the numbers now. It is about a fourth of the mass of the Milky Way, more or less. There are some studies in this direction. Okay, so it is much smaller than the Milky Way, but it is it's our companion. We are only 50 kiloparsecs from the LMC, so it is embedded in part of the stellar halo of the Milky Way. So it is crucial to understand the LMC evolution and its orbit with respect to the Milky Way, and take the Milky Way into account when studying the dynamics of the LMC. The SMC, I think it's about a tenth of the mass of the LMC. It's again much smaller. So if we only have the two bodies, LMC and SMC, imagine you have two bodies, and by gravitational attraction, the SMC is attracted by the LMC. But again, these two galaxies are attracted by the Milky Way. So in the Gaia EDR2, the community did the effort of computing the orbit of a number of dwarf galaxies in the local group to see their evolution, thanks to the proper motions, to see where are they heading, if some of them come from the same position, and all of these analyses. Regarding the bridge, it is, we can see bridges in external galaxies. You can see M51, we have these two very nice spirals connecting the companion with M51. We have the antenna galaxies. We have seen them in photometry, in density, in many of external galaxies. But I think that now for the first time, we have also to increase the dimensions, including colors and proper motions. And this opens a big window on studying the dynamics. We can have embodied simulations of interacting galaxies. We'll show you some results and the plans for some results. But we have now at hand the data to be able to compare to these predictions given by the simulations. So having the opportunity to study dynamically interacting galaxies, not only from the theoretical point of view, but now using observational data with all the limitations they may have. More or less.
Okay, so please, if anybody has a question now or wants to clarify some things, just raise your hand.
Everything clear?
I see a hand raised, but I don't. Who, now,
Either.
Paul. Paul,
Yeah,
please go ahead.
Okay.
I have a very brief question. You were showing the velocity distributions according to the different populations, and you were displaying how young systems seem to rotate faster. Am I correct? How? My question is, how is it compared to the Milky Way?
It is a typical behavior. This is what we expect for the Milky Way. It happens the same.
So it's okay. So
the problem with the Milky Way is that we are embedded in the Milky Way, and getting this whole range of radius into the galactic center, it is with different evolutionary phases. It is very difficult. We have more or less the rotation curve now with Gaia data between -3 + 3 kiloparsecs from the sun, but we are about 8 kiloparsecs from the galactic center. So with the rotation curve, the stellar rotation curve, it is very difficult to get until the galactic center, because we can get into the galactic center with infrared data, but then we do not have the motions, or we can have it in gas, but it has pros and cons. But the behavior with the populations, it is the same. It is a typical behavior.
So in this sense, you mean that the LMC and partially the SMC is somehow a better laboratory to study these kind of things?
Exactly.
Better than, okay. Thanks.
Okay, so then maybe we resume your talk then. There's no other questions. Thank you.
Okay, so this were the results shown in the paper, and then more or less at the same time, Oscar started his PhD thesis with the team. It's supervised by Xavi Luri and myself, and since then we started doing some preliminary work, trying to for him to get trained, to get familiar with the data and all this. We asked him to reproduce some results, get into this 3D structure of the LMC, getting familiar with the data and see how we can improve or dig more into the data. So one of the we had this kind of spine that we want to solve is this trying to infer the 3D structure. We tried during the time of the preparation and writing of the paper, but we had a strong deadline and we could not pursue the work. But now we have more time and we can try to do better. So we are. When trying to solve this problem, we have been using, or we are testing two different strategies. One is using approximate Bayesian computation, the ABC. The ABC method is based, as it says, in Bayesian computation, but it is called approximate because you know that in Bayesian computation we need to compute a likelihood function, but we do not have it in this case. We do not have an analytical likelihood function to evaluate. So the ABC methods bypass this difficulty and try to approximate it. And what we do is we have to assume, this is a drawback, we have to assume a model for the galaxy we want to infer its characteristics. And what we did is to assume a flat ellipsoid. We put it at a certain distance with some ellipticity, with a measured position angle, and a given inclination and position. And then these are the three parameters we use to simulate, to model this main structure of the LMC. We only try to reproduce LMC structure because we know this kind of this galaxy. So we do not, at this step, we do not include any bar, any spiral arms, only a kind of flattish disk. Okay, so the posterior of this statistical approximate Bayesian computation is this typical plot here. We can reproduce very well, or we can reproduce or recover quite well the free parameters we have used. Things to take into account. It is not computationally very expensive, but using some clusters, it has taken more than 4 hours. The other thing is that in this model, we do not have into account errors or uncertainties in the measure. So we just assume that we know exactly the position and the distance of these particles that form this ellipsoid, this flat ellipsoid. Okay, and then we define a metric, and then we try to minimize this metric. And this metric that we define is based on the parallax and the counts per bit. And the results in the 2D distribution. So on the first row, this is coordinates, XY coordinates on the sky. And the first row, it is the counts. This is the real, let's say, ellipsoid. And this is what on the right, what the ABC results. So we can see very well that we have more counts at the center, the decreases because of the profile that we have given to the model. And on the bottom row, the parallax, we have inclined the disk. So we have a distance gradient or a parallax gradient to be the near side and the far side of the simulated LMC. So this is the true, what we have modeled, and this is what we infer from the computation. So we were happy. Okay, the method works. The problem is that when we add uncertainties to these parallaxes, so again, now we have on the top row this same mean parallax. Now we include also the standard deviation of the parallaxes and the counts. And on the bottom row, we do the same, but when we have added uncertainties in the parallax of this model of the LMC. And now we can see here, you can see that the color code of the bars has changed. It has increased largely when we take into account the parallaxes. The counts we can more or less reproduce well, but it isn't the uncertainty on the parallaxes that makes it difficult. It is more or less what we found or what we thought that what could happen when making the paper, but now we have the clear reality here that the uncertainties in the parallaxes at these distances are damaging, are making the problem very difficult to tackle. Now we have a second strategy. So just need one more thing. In here, what we do is bin these particles. We have created the thing, I don't remember, we have the number of, I think it was 100,000 particles in this model ellipsoid, and we make the statistics in each per bin. So we compute the mean parallax, we compute the mean counts, so make the analysis in per bin. But now in the second strategy, we use a Monte Carlo Markov chain strategy. So this is in collaboration with the team in Madrid from the UNED, Luis Sarro, Ángel Beruete, and Héctor Delgado, which is also the PAC people. And they are also experts in statistical analysis and data mining. So the MCMC is based on star-by-star basis. Okay, instead of using analysis per bin, we made a star-by-star basis. So we have now to assume the model for the uncertainty in the parallaxes. We do not. The good thing is that we do not have to assume a relative model, but we need to know the uncertainty in this of that particle or that star at that position. If you go to the Gaia performance pages, there are models for the uncertainty in parallax, but they are assumed to be Gaussian. If they were really Gaussian at these distances, fine, this is easy, and I have mock catalogs for the Milky Way using these Gaussian errors. But what we do here is make it one step more realistic and not assuming Gaussian errors. And this makes the problem also more difficult and computationally more expensive. So, for example, we require some GPUs in order to simulate this the 1,000 or no 1,000, 1 million particles to give some uncertainties in the parallaxes, taking into account the 0 point and all this. So this is work in progress. We have more or less stopped the ABC strategy to see if with this MCMC strategy we get better results, which now it takes into account uncertainties. The other thing we have also invested some time is studying the kinematics in the bridge. I showed you before the two main plots we have in the paper, but now we kind of reproduced these plots and made a more deep analysis. And here are the results for the Young bridge. And I show you on the left the background plot is the density. So the top here is the SMC. The LMC is here on the bottom, and we overplot per bin the mean proper motion vector. And we can see again that here it is chaotic as the SMC regular motion has, but then here we can see a clear flow from the stars towards the LMC and then start rotating around the LMC. And now what we have done on the left we have the same plot, but you can see two arrows in red. One arrow has this typical motion around the LMC, and the one on the bottom, one of the bins that are in the middle of the bridge. So now on the right, we plot the velocity distribution in each of the two coordinates, so the x coordinate and the y coordinate. So here we have the x coordinate and the y coordinate, and we plot the median and some kind of fitting, smoothing this histogram, because, for example, for the Young sample, at these outer regions we have very few particles. Again, you can have the number. We have 13 particles, and here we have 29 particles. So we apply a kind of a smoothing. But you can see here we have the typical rotation of only one population. But here on the bridge, you can start with very few stars. I agree, but we can have, for example, for the x coordinate, we have a clear negative, so it has clear negative value. But for the vertical component, we may hint a kind of overdensity with positive values. So we expect negative towards the LMC, but there are some stars that have positive. So maybe it is another population. It's not only bridge stars that flow from the SMC towards the LMC, but maybe we have here contamination from halo stars, from the Milky Way, from the SMC, or from the LMC. But it could be a good way to filter and make a cleaner sample for the bridge stars. So this is for the Young bridge, and we can do the same for the old or more evolved red clam bridge. Okay, as I said, in density is more difficult to see, but in proper motions we can see here a clear flow from the SMC towards the LMC, and we can do again this histogram combination. Here we have more stars, and in the halo we have this typical motion on the halo, but you can see that for the bridge, this second peak that we hinted for the Young population, but we had very few stars. Now here it is clear bimodal distribution. So this is something that we are still studying, but it's more details that we didn't have before. And finally, for the spiral arms, at that time we didn't have much time to get much more than the overdensities, but now we have invested some more time to make some again, velocity distribution plots. But we trying to see not only general radial velocity and tangential velocity plots, but focused on how the spiral arms perturb this radial velocity and tangential velocity. So let me go one by one. On the left, again, we have this position, X and Y on the sky, and in color, we have the counts. We have applied a kernel density estimation to remove let's say the axisymmetric component and highlight the non-axisymmetries in the disk of the LMC. So you can see that now the positive values, so the more pink values, are over densities, and they clearly highlight the non-axisymmetries of the LMC. So we can have the bar and this spiral arm that goes around almost 360 degrees from the whole revolution around the galaxy. So now with this contour, taking into account this contour that highlights where the overdensity due to the spiral arm and bar, we transfer this overdensity to the plots on the right, in the middle on the right. So in the middle, I use the same, we use the same contour, but now the color is the radial velocity, so the motion towards the galactic center or outwards from the galactic center, and on the right, the tangential velocity when we remove the rotation curve. Okay, the rotation curve is the main motion of the disk. So let's remove the main motion of the disk and see what it remains, that it will highlight the motion of the non-axis symmetries. So we can see that we do not have a smooth homogeneous distribution for none of the components. So radial velocity, if the disk or if the galaxy was pure rotation, would be centered around 0, and we do not see any substructure. We do not see any overdensity, but we do see here a kind of cross. Negative, positive, negative, positive. We see an overdensity here, positive velocities here. On the arms, it seems to be negative here, but then it bifurcates and creates this overdensity here, and something similar for the tangential velocity. Okay, so we also have this positive, negative tangential velocity, typical for the bar motion. I'll show you in a minute. But for the spiral arms, it is more complicated to infer. So then we trying to interpret these velocity maps, we went into the simulations. We went to have the help of the simulations, and in this case, I show you the results from one of the simulations by Shervin Laporte. But we also have similar results from the other models of interacting galaxies, of spiral arms in galaxies, sorry, from a work by Teresa and Santi Rocafabrega and back in 2016. So let me show you, let me explain here. We have two different snapshots of the same simulations by Shervin at two different times, say 30 and 63. Where we have some initial conditions, they are evolved, and you can see that here we have two very nice grand design spiral arms at this stage. On the left again is density, and on the right here it is like double time of evolution. We can see a kind of bar here, a kind of elongated ring, and again one very strong spiral arm here and a smaller spiral arm here. So we see asymmetries in the distribution. And again, the plot on the middle and on the right is the radial velocity and tangential velocity. Tangential is like on the rotational velocity. So we can see that there seems to be a correlation between the overdensity of the spiral arms with the sign of the radial velocity. Careful, but because now the color code convention is different from what we used here. So here red was positive velocity, and here it is the opposite. But just to show you the correlation. In the top panel where we do not have a bar, we just see the overdensity or the correlation with the spiral arms. And on the bottom panel where a bar has evolved, we see this quadruple signal of positive, of negative, positive, negative, positive that we see also in the data. And the spiral arm structure is not so well correlated in this case with the velocity. It's more difficult to interpret. But if we would be able to overplot the density as we have done with the contours in here, maybe we can hint something, but it's more difficult to interpret. The same for the tangential velocity. Okay. So just to give you a comparison, I take the snapshot where we have a bar, because in the LMC it has a bar. Note that the purpose of this simulation is not to simulate the LMC. You can see that the LMC has the SMC, it has a strong gravitational interaction within them, so we should use a simulation of interacting galaxies. But just to help you to guide the eye in these signals that we see that depart from the axisymmetry, and trying to understand how these signals, for example, on the spiral arms, affect the kinematics of the galaxy. Okay, so this is my last slide, just a summary. When getting involved in this Gaia collaboration paper on the LMC and the SMC, we got very excited. It was a very nice science case for Gaia astrometry and photometry, opening the window that not only density plots could be used to analyze the data, or having only very few proper motions or very few line of sight velocities. Now with Gaia, we open the window to study the dynamics of the galaxies. We clearly see that the LMC is one spiral arm galaxy with disk rotation. The SMC is more irregular and it has no detectable rotation. We also open the window to use or to study these kinematics and dynamics using different tracers, young tracers, red clamp, Cepheids, Error-Lire. I haven't shown you the results here from the Cepheids and Error-Lire, but they are very promising as well, because with Cepheids and Error-Lire we have these light curves. We can use the period luminosity relation to infer distances much better than, with much more accuracy than parallaxes. So we are also working using these variability stars to study the structure of the LMC. The bridge and surroundings are very rich. We can now see that we can confirm the stellar counterpart of the gas bridge. And at least in the young population, the more evolved populations like red clamps or Error-Lire is more difficult to see, and there's still some controversy there. And that's it. So I think we have two galaxies that are good laboratories to study different aspects of the Milky Way, of interacting galaxies, and I think it is a topic that now it's become quite I don't know, interesting and appealing for people. And that's it.
Okay, thank you very much, Mercè. Thank you for this talk. And so then let's go to the next round of questions now to finish, please. Well, I don't see any questions so far. So maybe, Mercè, I will ask you about one of the things that you discussed was these motions along the bridge. And you had some arrows there showing, you know, what I guess it was the mean motion of stars at different positions in the bridge. And I didn't understand very well how that was being modeled. So, you know.
No, it is not modeled. This is just the data.
Yes. Okay. So relative to the LMC, Okay, so
yes,
this is
this is true.
and the SMC.
Yes.
There was one which relative to the SMC, and you looked at the bridge, and then you saw the mean motion.
Exactly. All of them are relative to the SMC.
Mm-hmm.
I think, no, for this case, I think, Oscar, we didn't have the proper motion of the SMC well constrained, and we made it relative to the LMC. But it's more, it's the same. You make it relative to one or the other, but it is the relative motion of one with respect to the other.
Okay. And you had, I think, a previous plot to this, which also had, I mean, the map was clear, more clear. Here, I think, yeah, there are these arrows, right? Which, I mean, shouldn't you see here basically the effect of the tidal interaction of the two galaxies?
Yes.
So I didn't follow exactly how we interpret those arrows here.
These arrows are just taking bins in this region and on all of these outer parts of the two galaxies, compute the mean proper motion, subtract it from the mean proper motion of their own galaxy, and just plot the arrow.
Okay, so why, I mean, around the SMC, it looks like everywhere those arrows are pointing toward the LMC. And then when you go to the middle of the bridge, there is a larger motion, right? The stars are moving toward the LMC. But why, when you go even, you know, to the sides and behind, there's always the same direction of this mean motion?
Well, I can tell you that here we have very few stars.
Okay.
Okay, so these are very few statistics. So, for example, in the plot where I show you our own plots, here in this one here we have 13 stars, and in this one here we have 29. At the other side of the SMC there are maybe still less. Okay, so I wouldn't believe much these arrows here. These are much more significant, but again significant of 30 stars.
Yes. So, but so you interpret this as
basically... But it is not only one star that signals towards the LMC, it's all of them.
Yeah, so it's all of them. So you interpret this as the tidal acceleration. So the LMC is pulling those galaxies in between the bridge towards it, right? Yeah. Okay, thank you. I think I see there are two more comments. There's questions in the chat.
I don't see the chat. Let me see.
Friedrich, do you want to ask your question directly, Friedrich, if you want?
Okay.
Can you unmute yourself?
Does the MCMC allow you to include the bar parameters and maybe also the spiral arms? We haven't tried yet, but maybe Oscar will tell you who's the direct contact with Angel if they have plans to do it.
By now, we are just testing with the data, so still no model is assumed, so I can't tell you anything more about that. Maybe we can try it, but no idea.
We were considering in this ABC, but when including the uncertainties in the parallaxes, we gave up. If just a disk, we can, the large uncertainties in the parallax, we cannot get the parameters of the disk. It's not worth trying, including a bar and spiral arms. But for the MCMC, we still have very preliminary results. We haven't done any massive test yet, so it's in the future. Thank you.
Okay, thanks. So
I think Blai has the.
I have yeah. Hi, Mercè. Hola. I have a question with respect to this plot you have been showing us, the Young bridge, and you have explained how these velocity vectors has been estimated or calculated. Okay. If I understood correctly, this is the velocity vector, which is the result of after subtracting other gravitational components, especially the one associated with the Milky Way galaxy gravitational pull, something like this, isn't it?
Yes, yes.
But what you are plotting here is this velocity vector which it is not clear to me if it's simply the component in the plane defined by the LMC and SMC, or is the full velocity vector. Because if I interpret correctly, there is also, let's say,
yeah, the line of sight component, we do not have it.
Perpendicular one.
No, we do not have it. This is just the components of the velocity vector on the plane tangential into the sky of the this position. We do not have the perpendicular vector, which is the line of sight velocity.
Okay. In that sense, just as a speculation, as there is also the gravitational pull of the Milky Way galaxy, maybe introduces a not well-defined component of this vector in the direction of the Milky
galaxy.
Way. Again, in the future, could modify this first results. I'm just.
I don't think so. Yes, I understand you, because we can see it very well in the gas, and in the gas we do have all the velocity vector, and the bridge in the gas goes exactly following this path.
Okay.
So I expect that just also speculating, that the line of sight velocity may have a strong contribution towards the Milky Way, but not biasing the tangential components or the transverse components.
Okay, hope so. Thank you.
I wanted to take the opportunity also to tell you that we have been awarded by an European project on cloud computing, and one of the science cases we want to do, or we've included in this project, is trying to have a focused simulation and high resolution simulation of interacting galaxies of LMC, SMC, like with the Milky Way contribution, to have these mock catalogs to be able to compare with the data. So this is a challenging problem, and I think with these dedicated simulations, we would be able to also help us interpret this data and if there are biases or not. And this will be this year.
Okay. Just a final question. What was the name of the dog that was barking?
Okay, the name
of the dog, of your dog that was barking.
This is Jordi's.
Maybe my dog. Yeah, when my mic was open, it is my dog. Yeah.
I don't have a dog. I have a son and a daughter, but I don't have a dog.
What's the name, Jordi's?
The name is complicated, but I can write it in the chat. And it is in the language that is called
Nahuatl, the Mexican,
and
native Mexican.
It means flower. But
okay, right. Thanks. It's a good point.
Sorry about that.
No.
Okay, yeah, she's here. Okay. Well, so it was a pleasure. Thank you very much. If there are no more questions, I think we can end here since it's already 1 o'clock. It was great to hear this, Mercè.
Okay.
Okay. Yeah. Thanks. And I guess till the next talk in the next academic year, the next ICCUB internal seminar, since that's the last one. Yeah. Good summer for everybody.
Thanks.
Have a nice summer. Bye.
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 Bye. Thank you.
Bye.